The night sky looks peaceful, almost static, a tapestry of glittering stars scattered across an endless black canvas. But beneath this serene appearance lies a universe in constant motion, galaxies spinning at incredible speeds, clusters colliding over billions of years, and vast cosmic structures stretching across unimaginable distances. Yet, when astronomers first began to measure how fast galaxies rotate, they encountered a profound problem, one that would shake the foundations of our understanding of the cosmos. According to the laws of gravity and everything we could see, galaxies should have torn themselves apart. Their outer stars were moving far too fast to be held together by the visible matter alone. But instead of flying off into space, they remained bound, orbiting smoothly around their galactic centers. This discrepancy gave birth to one of the greatest mysteries in science: dark matter. Dark matter is not something we can see, touch, or detect directly in the traditional sense. It does not emit, absorb, or reflect light, making it completely invisible to telescopes. Yet its presence is undeniable. Scientists infer its existence through its gravitational effects, its influence on stars, gas, and entire galaxies. One of the most compelling pieces of evidence comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When massive objects like galaxy clusters sit between us and distant background galaxies, their gravity bends and distorts the light traveling toward Earth, creating warped, stretched, or duplicated images. By studying these distortions, astronomers can map the distribution of mass, including dark matter, within these cosmic structures. Time and again, these maps reveal that visible matter makes up only a small fraction of the total mass. The rest is dark, silent, and mysterious. This leads to one of the most fascinating ideas in modern cosmology: the concept of dark matter halos. Rather than galaxies existing as isolated islands of stars in empty space, we now believe that every galaxy is embedded within a vast, invisible halo of dark matter that extends far beyond its visible edges. These halos act like gravitational scaffolding, shaping how galaxies form, evolve, and interact with one another. They are the unseen architects of the universe, dictating the large-scale structure of the cosmos while remaining completely hidden from view. Without them, galaxies as we know them might never have formed in the first place. In the early universe, shortly after the Big Bang, matter was not evenly distributed. Tiny fluctuations in density seeded by quantum processes created regions slightly denser than others. According to the cold dark matter model, dark matter, which moves slowly compared to the speed of light, began to clump together under its own gravity. Over time, these clumps grew larger and merged into massive halos, forming the gravitational backbone of what would later become galaxies and galaxy clusters. Computer simulations based on this theory show a universe filled with an intricate cosmic web, where dark matter filaments stretch across billions of light years, intersecting at dense nodes where galaxies and clusters reside. One of the most powerful tools for studying these invisible halos is gravitational lensing. It's often described as nature's cosmic telescope. Gravitational lensing allows astronomers to see dark matter by observing how it bends light. In cases of strong lensing, massive galaxy clusters produce dramatic effects in Stein rings, arcs, and multiple images of the same distant galaxy. These distortions act like fingerprints of the underlying dark matter distribution. By carefully analyzing them, scientists can reconstruct detailed maps of where dark matter is concentrated. Weak gravitational lensing, on the other hand, produces much subtler distortions that can only be detected statistically across thousands or millions of galaxies. By measuring how their shapes are slightly stretched or skewed, astronomers can infer the presence of large-scale dark matter structures. Surveys such as the Dark Energy Survey and upcoming observations from the Vera C. Rubin Observatory are providing increasingly precise maps of dark matter across vast regions of the sky. These observations consistently confirm that dark matter halos surround galaxies and clusters, often extending far beyond their visible boundaries. Perhaps one of the most striking confirmations of dark matter's existence comes from observations of colliding galaxy clusters, such as the famous Bullet Cluster. In this cosmic collision, hot gas making up most of the visible mass was slowed down by friction, while dark matter halos pass through largely unaffected. Gravitational lensing maps revealed that most of the mass remained aligned with the galaxies rather than the gas, providing some of the clearest evidence yet that dark matter is real and behaves differently from ordinary matter. Keyframe. The dance of galaxies within their halos. Inside these vast dark matter halos, galaxies perform a delicate gravitational dance.
Ow.
One of the earliest clues to their presence came from galactic rotation curves, the plots showing how fast stars orbit at different distances from a galaxy's center. In a universe without dark matter, we would expect stars farther from the center to move more slowly, much like planets in our solar system. Instead, astronomers found that rotation speeds remain nearly constant even at great distances. This flat rotation curve can only be explained if a massive unseen halo surrounds the galaxy, providing the extra gravitational pull needed to keep outer stars in stable orbits. Even more intriguing is the surprising uniformity observed among different galaxies. Despite vast differences in size, shape, and brightness, many galaxies follow remarkably consistent patterns in how their stars move. This suggests that dark matter halos play a fundamental role in regulating galactic behavior. They influence how gas collapses to form stars, how galaxies merge, and how they evolve over billions of years. In some sense, galaxies are not independent objects. They are shaped and guided by their dark matter hosts. Modern simulations have allowed scientists to visualize this process in stunning detail. In these digital universes, dark matter forms large, lumpy halos, while ordinary matter, gas, dust, and stars falls into their gravitational wells. Over time, rotating disks form, spiral arms emerge, and complex structures develop. These simulations show that without dark matter, galaxies would look very different, or might not exist at all. The interplay between dark and visible matter is what gives the universe its rich variety of cosmic structures. When we zoom out far enough, the universe stops looking like scattered galaxies in empty space and instead resembles something more like a vast, glowing network. This is the cosmic web, a colossal, interconnected structure made of filaments of matter stretching across billions of light years, with dense nodes where galaxy clusters reside and enormous voids where almost nothing exists. At first glance, this might seem like a random pattern, but it is anything but chaotic. It is the direct result of dark matter halos sculpting the universe over nearly 14 billion years. Dark matter halos act like the invisible scaffolding that organizes cosmic structure. In the early universe, tiny density variations in dark matter grew under gravity, pulling in surrounding material. Over time, these regions became massive halos, which then attracted gas, dust, and eventually formed galaxies. On the largest scales, these halos connected through vast filaments, creating the intricate cosmic web we observe today. Without dark matter, this structure would not exist. Ordinary matter alone, interacting through radiation and pressure in the early universe, would not have been able to collapse efficiently enough to form galaxies in time. Every galaxy we see, including our own, Milky Way, sits inside a dark matter halo that is itself part of this greater cosmic web. These halos are not isolated. They communicate gravitationally across immense distances, influencing how galaxies move, merge, and evolve. When galaxies collide, it is not just a clash of stars and gas, it is also a merging of dark matter halos, reshaping the local structure of the cosmic web. In this sense, dark matter is not just a component of the universe. It is its primary organizer. Observations from large sky surveys have revealed just how dominant dark matter is in shaping large-scale structure. Maps of galaxy distributions align strikingly well with predictions from dark matter simulations, reinforcing the idea that what we see is merely the luminous tip of a much deeper invisible structure. The cosmic web is therefore not just a visual pattern. It is a record of how dark matter has guided the universe's growth from infancy to maturity. What halos tell us about the universe's ultimate fate understanding. Dark matter halos is not only about explaining the past, it also holds the key to the future of the universe. The way these halos behave, interact, and evolve over time can tell us a great deal about the cosmos's ultimate destiny. One of the biggest questions in cosmology is whether the universe will expand forever, slow down, or eventually collapse in a big crunch. Dark matter plays a crucial role in this equation. While it provides gravitational attraction that binds galaxies and clusters together, another mysterious force, dark energy, appears to be driving the accelerated expansion of the universe. The balance between these two invisible components will determine our cosmic fate. If dark matter were dominant, gravity might eventually slow and reverse cosmic expansion. But observations suggest that dark energy currently outweighs dark matter on the largest scales, meaning the universe is likely headed toward a cold, lonely future. Galaxies will drift farther apart, the cosmic web will stretch thinner, and dark matter halos themselves may become increasingly isolated. Over trillions of years, star formation will dwindle, black holes will dominate, and the universe could approach a state of near darkness. Yet, studying dark matter halos gives us deeper insight into this process. Their distribution and behavior help cosmologists refine models of how structure will evolve in an expanding universe. Some theories suggest that in the far future, only the most massive halos, like those containing superclusters, will remain gravitationally bound. While everything else drifts away beyond the cosmic horizon, there is also the possibility that dark matter itself could behave differently than we currently assume. If it interacts more than expected, or if new physics emerges, our predictions for the universe's fate could change dramatically. In this sense, unraveling the nature of dark matter is not just about understanding what the universe is made of, it is about understanding where everything is ultimately heading. The ongoing quest, humanity's greatest scientific challenge, the search for dark matter is one of the most ambitious and profound scientific endeavors in human history. It represents our attempt to comprehend something that is everywhere yet completely hidden, something that shapes our reality while remaining beyond our direct perception. This quest spans multiple fields: physics, astronomy, cosmology, and even philosophy. On one front, scientists are building increasingly sensitive detectors deep underground, shielded from cosmic radiation, in hopes of catching a rare interaction between dark matter particles and ordinary matter. Experiments like LuxZeppelin and Xenont are pushing the limits of precision, gradually narrowing down what dark matter could be. Each null result does not mean failure. It refines our understanding and rules out incorrect theories. In space, telescopes and observatories are mapping dark matter through gravitational lensing with unprecedented detail. Projects like the Vera C. Rubin Observatory, Euclid, and the James Webb Space Telescope are helping us see how dark matter halos formed and evolved over cosmic time. These observations allow scientists to test whether our current models of dark matter truly match reality or need revision. Meanwhile, particle physicists are searching for dark matter at the smallest scales. Using powerful accelerators like the Large Hadron Collider, by smashing particles together at near-light speeds, they hope to create conditions where dark matter might briefly appear. So far, the universe has remained tight-lipped. But the search continues with ever greater sophistication. Beyond the technical aspects, the implications of solving the dark matter mystery are profound. If we finally identify what dark matter is, it would revolutionize our understanding of physics, potentially revealing entirely new particles, forces, or dimensions. It could reshape our view of reality itself, much like the discovery of atoms, relativity, or quantum mechanics did in previous centuries. There's also a deeper, almost existential dimension to this quest. Dark matter reminds us that most of the universe is invisible to us, that our senses and instruments only capture a small fraction of reality. By studying it, we are not just expanding scientific knowledge, we are expanding human awareness of what exists beyond our immediate perception. Dark matter halos are more than just a scientific concept. They are the silent foundation upon which the universe is built. They shaped the birth of galaxies, organized the cosmic web, and continue to influence the destiny of everything we see in the night sky. In many ways, they represent the unseen legacy of the cosmos, guiding its evolution long before we ever existed as we move forward in this grand scientific journey. Each discovery brings us closer to answering some of the deepest questions humans have ever asked. What is the universe made of? How did it come to be this way? And where is it ultimately going? Unraveling the dark matter enigma is not just about solving a puzzle. It is about understanding our place in a vast, mysterious, and profoundly interconnected cosmos. And when that moment finally arrives, when we truly crack the code of dark matter, it will mark not just a scientific breakthrough, but a defining moment in human history.